hopefully by then we'll have actual in-person meetups.
Yeah, that'd be great.
The only thing we need to do now...
Adrian, have you now completely settled for just virtual meetups so that you can...
No, I very much miss the real setup. I was thinking the only thing we need now is really a venue where we can fit like 70, 80 people with 1.5 meters distance. And then we can have a meetup. Because probably from the 25th, there is no number of people restriction, right?
Yeah, my new employer may be able to help with that.
Yeah.
We are live on YouTube now, by the way, so just letting you know.
Do we have people on YouTube watching? Can you see that?
17.
Oh, cool.
Yeah. Okay.
Since we have no other topic to talk about right now, going back to the classical weather, do you really think this weekend it's going to be rainy? Last weekend it lied, and we didn't plan, and it was sad.
Do I really think this weekend is going to be rainy? We've planned a kind of a hall fest in the house for Saturday. So I think Saturday the weather's going to be lovely. Regardless of what the weatherman says. And if you look at the weather report, I mean, it's less of a question of what do I think and more a question of, well, what does the forecast say? Or I don't know. I mean, if we're lucky, there's someone with a background in meteorology here, and they can actually estimate that much better than I can.
Yeah. When I was in Vancouver, our estimate was that random, like an algorithm giving random output will probably be better than the forecast.
Did you test that?
No, but it was always wrong anyway. We tested in real life that it was always long.
When were you in Vancouver? 1960s?
No, but almost 10 years ago.
Okay. Yeah, I don't know. I'm tempted to make a comment about the great speed of progress with machine learning and all of that, but I noticed just today that there's I don't know if people are familiar with the Hugging Face PyTorch library for various different NLP tasks. I noticed that there's I didn't count them, but I scrolled through like pages and pages of model file names. The group at the University of Helsinki who does computational linguistics, they've released machine translation models for like, it must be like 100 different language pairs. So that's fun. I'm going to be translating some Finnish in the future automatically.
Hasn't translation in Finnish been notoriously terrible, the machine translations?
Yeah, I tried that already. Like I just did a couple of like quick tests translating Finnish into English. It was okay. It was like the English was still understandable, and it was pretty accurate. It was a pretty accurate representation of what the Finnish sentence was, or the paragraph.
I feel like you're setting a really low bar for machine translation.
Okay.
I mean, you're the NLP person. Maybe that's just like what you expect. But I expect to be able to have a conversation with people when I use machine translation, and like that not sound funny.
Yeah, I think you should be less worried about sounding funny and more worried about sort of catastrophic misunderstandings.
Oh, like the funniest thing I actually encountered was we had a customer, a Spanish-speaking customer in, I think, Central America, and a Spanish-speaking employee. And the voice was, I think it was like by Zoom. So the voice was transcribed and translated into English. And you would read that and you would understand like very well what the customer is saying. You could not understand what the employee says. So I don't know if it was like the English transcription from different accents different, but like it had some translated thing. It was probably like a different Spanish dialect. I don't know if that exists.
Yeah.
Or, I don't know.
Well,
Yeah.
keep in mind that in Mexico you have 66 different languages that are similar, some of these. Only in Mexico.
Okay. Okay.
So it might sound like Spanish or similar, but because of dialect or something, it might be totally different.
I mean, one problem that I always have in evaluating the machine translations, especially from Finnish to any language, but Finnish to English mostly, is that I tend to read the English translation with knowledge of what the Finnish original said. And then I kind of read in some or like, it's very difficult for me to judge how much I'm reading into the translation and how someone who's not a native Finnish speaker, how much would they actually understand of the translated text?
Yeah.
But often it's like, you read the translation and you go like, yeah, you can make a goodwill sort of guess on what was actually said, but it's not poetry, and it's not quite even at the level of like, here's some prose.
But is it the same with Hungarian? Because Hungarian and Finnish are in the same group of languages, I guess.
Yeah, but I don't speak Hungarian. I have no idea what anyone who speaks Hungarian is saying, so I can't judge. There is a really interesting aspect with like Finnish and Estonian are also very closely related, and there's a lot of words that are shared but have different meanings. It's the same word, it just means a different thing.
When you talk about Estonian, this is where I have to join.
Yeah, very good. But that very, very often throws me off. Like with I mean, I don't speak Estonian either, but I understand like, I don't know, 15% of the words, but then I understand them wrongly because they mean a different thing in Estonian than that same word would in Finnish.
Yeah, this is with the word hernia in Estonian, it means something bad. In Finnish, hernia means hernia, but you speak it in different way. So it's important.
Yeah. Yeah, I mean, okay. I would love to talk about language for the entire duration, but I guess that might get a little bit boring for others participating. So it's almost 7:05, and I guess we can start. So welcome everyone to the June 2020 PyData virtual meetup. This is now, what are we, fourth virtual meetup already? I think so. We're getting better at doing this. The meetup that is happening in Zoom is also being live streamed to YouTube. And I believe we have at least some number of people also watching the YouTube stream. It seems that we have 45 people watching the YouTube stream at the moment. Okay. So, and we have two speakers, Karol and Andres. I'm going to avoid saying the last names because I cannot say the last name of the first speaker in any kind of a meaningful way. So Karol and Andres, and we're going to have a little break in between. What we have done in the past with questions is if you're on the Zoom meeting, you can, I don't know, write your question down or write the question in the chat. If it's a longer one, if it's a yes/no answer from the first speaker, then he said that he's happy to just deal with it right away. But we'll try to save all the questions to the end and then go through those. If you're watching the YouTube live stream, there is a chat in the YouTube on the live stream page. You can write your questions in the chat, and we have Misha moderating the YouTube chat, and then he's going to try to pass those questions onto the Zoom call. The YouTube live stream, I believe, is about 10 or 15 seconds. There's a 10 or 15 second delay, so that may cause some issues. And okay, that's pretty much everything I wanted to say to begin with. But before I give way to our first speaker, there's one thing I want to just share my screen because I want to show something, but I need to, okay. I can't share my screen because I need to quit Zoom and do all kinds of things with the privacy settings here. Okay, so there is a PyData global meetup, conference that is being planned. The website for that is live since, I don't know, 2 hours ago, something like that.
Very recent.
So if you go to global.pydata.org, you will find more details about the conference there. It is a virtual conference that is happening in 4 different time zones simultaneously. There will be an open call for proposals. The CFP is not yet live, but we're hoping to get it live very soon. So if you just monitor, if you're on Twitter, you can follow PyData or PyData Berlin on Twitter, or you can just keep refreshing the website to see when the CFP is open. But it should happen within the next week. Okay, that's all I wanted to say about that.
The challenge. Don't forget the challenge.
Oh, challenge, right. So we have a challenge. Have we sent out the stickers? Do you know, for last month?
Noah is more familiar with that, but I remember the challenge.
Okay. We'll ask Noah about the details when she joins a little later. So there's a challenge. Who is the furthest away joining the meeting? Jim is a pretty good contender. Are you in Austin at the moment?
Austin, Texas, in the United States. Yep.
Okay, Austin, Texas. But I'm pretty sure there's going to be someone who's further away. So if you're in the Zoom call, just post your sort of rough location. I don't know, country and city should be enough on the chat. If you're on the YouTube channel, same thing. And we will, the person who is, how did we do this? Direct flight distance?
I think we just did the great circle distance on the Earth.
Great circle distance on the Earth.
Yeah, there's this page, distance from to.net, and I'll use that for.
Don't tell them that. They're gonna go there and cheat.
Okay, I'm not using that.
Yeah. Exactly. Yeah, so the person who's the furthest away from Berlin, Germany, we will send you some PyData stickers. So yes, definitely worth participating. Right. I am in Berlin, Germany. Me too.
Close.
Yeah, close. Maybe next time we do who's the closest. Right. Okay. Sorry, I'm going to stop talking now. Karol, please go ahead.
All right. Thank you. Thank you for the introduction. I will talk about skin cancer today. So a very serious topic. I hope you can see my slides now. So I will show you some computer vision methods, but in general, I will talk about skin cancer, how to approach this topic of skin cancer, machine learning, computer vision. Because this is what I'm doing for, I don't know, 13 years now. So skin cancer analysis. But before that, let me just introduce myself. My name is Karol Przystalski. Yes, it's a very hard name to pronounce. And well, what I'm doing machine learning for about, let's say, 15 years more or less. I even obtained a PhD in this topic at the University, specializing in skin cancer, so health tech. Not only the PhD thesis is about skin cancer, but I'm also doing different projects in the area of health tech. And now I'm the CTO and the founder of a company for 10 years now that is actually also doing some analysis in this topic. Work. I have experience in different kind of areas, like Stanford University, for example, where we have developed an asthma solution together with Stanford, or currently the COVID case that we are actually also analyzing data for the COVID discovery, and different kind of companies. Some of these are actually also from Berlin. All right, that's a short introduction. What is the current state of melanoma? What's melanoma? Actually, the level of this presentation is very, very basic. So I will try to explain all of the, well, hard words potentially. Like melanoma is the skin cancer, one of the skin cancer. There are several different skin cancers. Malignant melanoma is one of it, and this is one of the most dangerous skin cancer. So what is the current state? So what is the problem that we would like to solve? So the problem is not really replacing the doctors, the medical doctors, the GPs and diagnostic. So the goal is to support the medical doctors. What I'm saying about the problem, because of my research, now what we are doing now, we are commercializing this solution. So we are trying to push it to the market to make it available for the doctors, not only for research but also for the doctors to potentially increase the accuracy, increase the sensitivity, increase the specificity. So increase the quality of the diagnostic of the medical doctors. And there are different solutions how to solve it. One of the most basic one is actually to find out if on the image you have it's a skin cancer, it's a melanoma, or maybe it's something else. It's not really, it's an illness, or a case that is not really malignant. So it's a binary distinguished problem, a binary classification. Or what we can also do, we can actually have a multi-class problem where actually we would like to differentiate or try to find different kind of illnesses, and including melanoma. So melanoma is not the most popular skin illness when it comes to the moles, but it's the most dangerous. So obviously we would like to keep on focus on that, but we would like to also find out if there is if the mole is something different. Or what we can also do, we can implement one of the melanoma scoring methods. A scoring method is a method used by the doctors to find out if it's a cancer or not. They just go through some metrics. I will explain it later during the presentation. I would give you some kind of a medical knowledge, share with you some medical knowledge as well, explain it. So the scoring method is something that it's a method that the doctors use to find out if it's a cancer or not, and they take some of the features that are visible on the image. Or the last solution is to find patterns. What does it mean? There are some specific patterns of melanoma or different illnesses, different moles, not only melanoma, and you can find out and try to figure out if it's a malignant case or not. Well, when I started my research in skin cancer at the university, so many years ago, in 2007, so 30 years ago, I asked one of my colleagues at the university to share the data set of the moles that he actually had, and he gave me 47 images. So you can imagine 47 images. It's nothing really to do any kind of research, and this was the situation 13 years ago. Now you have different kind of data sets. The most popular, ISIC, which includes the HAM 10,000 data set as well. It has about 34,000 images of different moles. That's a huge data set. 13 years ago, it wasn't really possible to get such a data set. It's really going in moving in the right direction when it comes to the availability of data. And it's public. You can download it and do your research on melanoma. And even ISIC is publishing challenges, like Kaggle is doing it. So Kaggle also publishing challenges. ISIC is dedicated to melanoma. And every year there was a challenge, there's a competition to find out different kind of cases. It's not only about strictly melanoma. There are some image pre-processing challenges as well, and that's now it's available. So what I did, having just less than 50 images, I asked several institutions, dermatologists, to share the data set, and finally I received a data set of 5,000 images that I based on doing my PhD. With 5,000 is enough. It's not enough to actually do a, potentially it's not really enough to do a deep neural network, but it's good to do the shallow methods, implement the shallow methods using this size of data set. With 34,000 images that you have on ISIC, it's easy to do any kind of method. I will show you one of the solutions that is already, it was the winner of the challenge from 2019. Oh, it's loading. Sorry. Yeah, it's loading. Okay, never mind. So the competitions on the melanoma, it started in 2016. So actually, after 1 year before I finished my PhD, the goals mostly in 2016, 2017, 2018 were about segmentation, feature extraction, classification, because the data set, it wasn't so big like it was now. It was about 5,000, about 1,000. It actually increased each year. Now we have 34,000. The last challenge was not about feature extraction, but it was about classification, not a binary classification. It was about multi-class classification for 9 different illnesses. There are more illnesses, so skin illnesses. So we have a multi-class problem with 9 classes, which is quite complex. But that's really nice. And just here we have the ROC curve, which does give better understanding how good we are on finding different kind of illnesses. You see melanoma here with mel with the blue is here the chart mark. So we are not yet there, right, to be perfect on finding this skin cancer, the most dangerous skin cancer, right? Because there are different kind of cancers and different kind of illnesses. Not all of them are cancers, and you see that are some unknown cases that are, it's almost random. right? So we are still not there. Most of the solution that will apply to this challenge based on convolution neural network to find patterns based on the images. What is important to mention is that the data set that is here at ISIC is based on typical classic dermatoscopy images. I will explain you later what's the difference between a multi-level and dermatoscopy one-level image. But we can see that actually is increasing the number of research papers. This one is based on ScienceDirect.com, and you see that the number of papers published in the topic of melanoma and artificial intelligence is increasing. It's not going in thousands, but if you go to the ISIC challenge, most of the results of the teams that actually published the result, they have also published a paper on it. So that if you combine Science Direct with Springer, with all of the other publishers, the numbers should be much bigger. But you see, it's growing. It's growing in the last year, especially now when we have the COVID and we would like to automate many actions, many procedures that you do. Obviously, we cannot automate it totally. Still, there need to be a person behind it to take the diagnosis. So that's the current state. What are the challenges? In my opinion, there are two big challenges that I think we will focus in the next year. We should support the general practitioners, so that medical doctors that are not specialized in dermatology. So it means they're general medical doctors, and I mean for more typical illnesses, but they don't really have a specialty in the dermatology. So they are not really good at finding skin cancer. You can imagine that the sensitivity of such doctors is something between 50 and 60%. So that's quite low. And the challenge here is to find a solution that will support this kind of challenge, this kind of GPs, to find out, to increase the sensitivity, specificity, and obviously accuracy of GPs, because the medical doctors, the dermatologists, that specialize in skin cancer, they can reach even 80-85% of sensitivity, which is quite high. And the second challenge that I think that we have, that will come in the next year, is to detect melanoma not only on the skin, because melanoma is a cancer that it's not really only on skin. It can happen on the eyes or on the nails, which is much more difficult to find. Or you have also kind of special kind of skin cancer that is transparent. You can imagine how hard it is to find a cancer if it's transparent, right? So that's a challenging task for the researchers, also for the doctors, for the medical doctors. All right. So I will talk about a bit, because we want to approach the get to the market with the solution. And if you deal with any kind of health tech product or solution, you will probably face the problem of FDA requirement and being approved with your solution to the market. It's more about, this is more like more like a lawyer stuff, but just few slides that I would like to explain, because that's something that we are now facing. So if you have an AI solution that is supporting the doctors, you need to get an FDA approval, or the same actually in Europe, but in general, you cannot just use it on the market. You need to have an approval to get to the market. It's regulated. And it's called, in US, it's called the 510K process. You need to get this kind of approval to go to the market. And usually, in not all, but actually almost all cases, it comes with a medical device. So it's not just a software, it's coming with the medical device, and it's sold also as a medical device. And the FDA regulation, they tell us that on the website that it takes up to 90 days to get the approval. To be honest, it doesn't work like that really. Usually it takes about 6 months to get to approval because they have many questions in the meantime, and they will ask for more details on the algorithm. So I would tell you some more about how to prepare for this kind of approval as well. And the biggest challenge here is the clinical evaluation. So you need to find out if your solution, so SAMD is the short name for software as a medical device. So it's a AI, I mean machine learning solution that comes together with a medical device, like a dermatoscope, for example, which is the most basic device for the doctors that they are using for the diagnosis. And the clinical part can take even up to 2 years to find out if your solution really is able to increase the accuracy. And you have 3 stages here. So we have the but in general, it takes a lot of time to really do this part, and you need to involve also the dermatologist in this phase, and also obviously patients that will use your solution. So the whole process is very difficult. I will not. You have some sources, so I can send you the link. You will get the presentation, so you can check the links here. Go to the FDA webpage to find out how it works. But in general, it's written. The document that they provide is written in a way that it's very hard to. It's written well, but it's really hard to. What's good machine learning practices, right? It's a term that they use in document, and obviously we as data scientists, as machine learning experts, we know what are the good practices, but still that's not enough. What they want to have, I mean the FDA, and what you need to think about from the beginning is to have the models explainable. So they need to be explainable, and obviously if you do a modification, right, then you also need to have an acceptance. So let's say you need to do a retraining of your model, and it takes also time to make. Sorry for the quality of this image. That's something that I downloaded from TMF. We see an increase in numbers when it comes to the AI machine learning solutions introduced in different kind of areas, not only in dermatology, not only in skin cancer. There are different kind of areas in medicine that where actually it is used and is approved. I mean, the FDA approved the so-called artificial intelligence-based algorithms. Okay, so that's the missing image here that I have here, right? So the missing image that you don't see here, but I have it on slide. For now, when it comes to the skin cancer, there are 2 companies having an FDA approval. One is from Germany. They are called PhotoFinder, and they have an FDA approval for a convolution neural network. As you know, a convolution neural network is explainable, so they are able to do it. And a second company that is called Canfield. I don't know really what method they use, because they only announced it that they use AI, but I didn't saw it work in practice. So it's very hard to say, but they say that they are using it, and there are more and more companies that will get an FDA approval probably soon. Like Heine, for example, also a German company that probably will also introduce our machine learning solution. And what is important here are the explainable artificial intelligence methods. And what I would like to tell you here is just go through very, very shortly, because the main part, the computer vision part, comes in a minute. That you should focus when you do a health tech project. You should focus on explainable AI, on explainable AI methods. So interpretable artificial intelligence, responsible artificial intelligence, and there are different kind of characteristics of explainable AI. But in general, there are understandability, comprehensibility. In other words, whatever you develop, you should think about the model in a way that it should be explainable, understandable by a human being, not only by the method or by, I don't know, the data scientist. It should be explainable, and that's very important to include into the FDA process. And also interpretable, explainable as well, and transparent. Very, very important characteristic or very important topic, the transparency. So what's going on in there? And there are three different levels or different ways how we can make the model transparent. The first one, we can simulate the process as a human being, and meaning we can set it, for example, as a set of rules to go through and actually give it to a human to go through. It's easy to explain, and it's also easy to be approved by the FDA. But it's very hard to develop really good models that are totally simulatable, that you can are able to simulate the whole process, and it's very hard to find such a models to be good when it comes to accuracy. The second level is decomposability. It means we can decompose, we can find out, get the whole model decomposed into a few different parts, and try to explain each of the parts separately, or at least the most important one. For example, if you have a neural network, you can try to explain a part of it. Like the convolution neural network, right? You don't need to explain all of the weights that you have, but at least you should explain the main idea, what's behind. I will show you an example in a minute how to do it. Or algorithm transparency. So it's not only it's not only about simulating it, but it's we have, for example, an equation. It is usually it's a linear model, usually like a linear regression, for example, where it's easy to reproduce the whole process. So it's not a set of rules. It's not exactly easy to do a simulation. I mean, okay, in the case of linear regression it is, but there are some models that are linear that are not so easy to simulate, but it's easy to use the equations to make it explainable, like, for example, SVM might be one of it. So there are many reasons why to use explainable AI. For us, the most important thing is obviously the regulatory agencies to be compliant and be able to sell the product at the end with the hardware. So we are not producing the hardware, obviously, as a company. We are building the machine learning solution for that. But obviously, also explainable AI is one of the way how we can also debug why it happens like that. And there are many failures, cases of failures where machine learning models failed, and explainable AI might be one of the solutions to explain why it happened like that. So the goals, there are different kind of goals, obviously, of an explainable AI. Like, we want to have a robust, clear, understandable model that is understandable by domain experts, right? But also, what is important, we don't want to know what's the importance of the features, for example, right? So there are also different other goals like informativeness, confidence. That's clear here, I guess. So we want to know what's actually information behind it, or even transfer it to a different case, right? Or even interact with it. You probably have heard about some cases like the Thai chatbot, tweetbot, or you have probably heard about the case about the gorillas in Google. That's something that is not really fair, and that's also one of the goals, to have a model that has an well, keep the privacy, but also is fair for the users that use this model. So there are different ways how to explain it, how to make the explanation for the FDA as well. So text explanation is the easiest one for us as the researchers, using formulas, equations, symbols, text. That's easy. For people who are not really good in math or doesn't understand what's in the back, in many cases the visual explanation is a better one. To visualize, for example, for a chart with a plot, how does it work in the back, or a local explanation. So take just a part of the whole problem, and let's say if we have a skin cancer, so we can take just, for example, one layer of the image and try to explain it just based on that. I will show you also one example here in a minute, or explain by example, like putting some different images, like cancer, non-cancer, and what is happening with the data on the input during the whole process. Or simplify, for example, if it's too complex. If it's too complex, we can build a model. There's a simplified version of the complex one and try to explain in this way. Or the feature relevance, that's the most basic one to find out what are the features that has actually an impact on the model. Okay, so one of the case is here, this is the melanoma. Here you have two images. You can imagine which one of these is a cancer, right? One on the left or one on the right. So in this case, I know because I studied this topic for at least a few years. It's obvious that the one on the left here, so this one here is a cancer case. Why? Because it has some dots here. You have, it's not regular, and so on. And also the medical doctors that will do the analysis, they will also focus on some factors like the dots here. It's called the pseudodots. It means that actually it's going deep into the skin, into the blood vessels, and that's dangerous. Also here the black stripes here, it's also not really, it's also a pattern that's specific for cancer. This one here on the right, it looks on the first look like a, well, not the prettiest one, but this one is not a cancer. This one is not a cancer. It's quite regular here. We have kind of a net here, surrounded, and then a black part of in the middle, but that's not a cancer. And using computer vision, we can or machine learning or pre-processing methods, image pre-processing, we can find out this kind of patterns and find out if it's a cancer or not. But also there are also some cases where I'm giving here IBM because IBM have developed a solution in the past that was about giving advices for the patients, and actually they totally failed with the advice that they gave by with our automated solution using some machine learning methods behind it. So it's not always good to there are some cases where actually you can find out it doesn't work so well. So you need to be aware that that's why also the FDA is here used to really check what's going on behind. So white box model, again, these are the models that are easy explainable. So we have the input, we have some, let's say, a decision tree. We know exactly what's the rule are, we know what's in it, and we know the output. Like, for example, a linear regression. That's easy to interpret, that's easy to explain, even for a person who doesn't know what's a linear regression, right? And that's one of the methods you can use for your model, for your case, if you're doing a healthcare. But obviously, linear regression isn't really so useful in this case. So you can use decision trees, or you can use also SVM, for example, right? And obviously, what's the explainable AI I mentioned already. So we would like to have information about the importance of the features, or how the features affect the prediction, for example, or understand the big picture of the whole thing. And there are also other ways why we should, or what cases where actually we can use explainable AI to debug the model, to improve some of the features engineering process, and many other cases, like eliminating overfitting, for example. Like debugging, we can find leaks, data leaks, or validation strategies, for example. All right, so feature engineering. Feature engineering, that's something that is makes sense for shallow methods, because if we use usually a deep neural network, then usually it's not something that we just give the image as the input, so we will not really get the features out of it. Instead of that, the network will try to give us the information about the features, like in the convolutional neural network. Comparing to white box, you have also black box method where actually you know exactly what's in it. It means you have a method that you are not able to explain. And let me show you. Okay, these methods are like decision regression, k-means, decision trees. These are actually easy to explain, like the SVM, for example. Let me show you one notebook. You have also notebooks available on the GitHub repository. Let me show you the difference between the black box method and the white box. I hope you see my screen now. So the black box method, this is a very easy, very simple neural network with just 3 layers here. So 3 dense layers with Adam as the optimizer, 2 ReLU functions, and 1 softmax, obviously, at the end. And we are fitting in with Keras here. But if we would like to explain what is the meaning of the weights here, this is how you can print weights from a layer. In this case, it's the second layer. You will get something like that. That's not something you can really explain. There are too many weights, even in such a not really deep network, because we have only 3 layers. It's not so easy to explain. So there are methods how to explain it, so make it explainable even on a neural network that is not explainable on the first look. Obviously, I have also the white box methods, like the decision tree, for example. And you will, even if you are not really a specialist, if you don't really have experience in machine learning, having such a information, such a visualization like that, if you know what's x2, x3, if you change it to the feature name, and if you don't know really what's the Gini index, you still are able to find out what's here, how to actually move from a tree to a set of rules that we are able to simulate or go through and actually get the prediction. So that's a white box method. Not all decision trees are white box methods. For example, I mean, decision tree, yes, but random forest, it depends on the level of complexity. It might be considered as a white box or black box method. So in case of health tech, like we have here, we usually should use a shallow method or a explainable method. If it's a neural network like this one, we will talk about we need to add some explainable AI method to explain it. And there are different kind of methods to explain the model that you have built. Obviously, if it's a shallow method, if it's a linear method, then it's easy. You don't need to actually use any kind of explainable AI methods to make it explainable, because it is already explainable. It is something that you can use directly. But there are a few groups. One of it, the based on the feature influence on the result, on the output, or explaining just directly the output, what's on the output, what does it mean, and so on. Or the neural network feature extraction method. That is a commonly well-known method in convolutional neural networks. Okay, I don't see any questions so far. Oh, there are 2. All right. So there is one really nice book on explainable AI. I will not go through all of the methods because we don't have enough time. But there are few like the PDP plots or Shapley values or scope rules or Lime. If you use the Python package tool, package management tool, you will find out that actually for all of these methods here, you have a separate library that you can use directly to find out, to explain your model. So Lime, for example, or Sharp, it's already implemented. Just to give you one example, how does it look like? Here's an example from this book here that I can recommend you for explainable AI, that you can use. For example, what's the influence from temperature to humidity and wind speed on the number of sold bikes, for example, right? So you can find out just drawing this kind of a plot. It's actually limited because we are kind of limited to our number of features, like 2 or 3 dimensions. We can add not really more. So that's a limitation. But on the other hand, it's very easy to interpret this kind of a chart. So we try to, based on the features, find out what's the impact of each feature on the prediction. So not only correlation can be used. There are some more sophisticated methods like the BEP, for example, plots. For scope rules, actually we try to find answers. So this is the line method here, to try to find distinguish between the outputs, even we don't really know what's actually the model about. So based on the output, we try to find out some methods or the scope rules that are tried when actually the method tries to find some areas that are specific. That in this area we have only positive or negative cases, and try to explain based on that the output. Right. So it's also easy to interpret. Many parameters to set. That's quite heavy to compute, but it's one of the methods. What's the noise in the audio?
1 second. And now?
Yes.
All right. Sorry. Okay, let me go back. Sharp limit values, that's a combination of different kind of features. If you change the number of features, do different kind of combinations, it might give us a better understanding. Is a better understanding what is the impact, and that's the method is called Shapley values to get a better understanding of the combination of the features to get a better understanding of the impact. Heavier compute, easy to explain, clear. Or the CAM, right? The class activation map used in convolutional neural networks. So convolutional neural network, why they are widely used also in melanoma, it's because it's easy to understand what is the output. So we actually calculate a gradient on the one of the last layer to find out where actually what features or what part of the image has the biggest impact on the prediction at the end. So that's something how we can explain the convolution network. We generate a heat map that if you combine it with the original image, we will get something like that. And for the classification, that's done actually on ImageNet. If you get the prediction like golden retriever, which is true, you will find out, oh, okay, so the ear, the nose here a bit, maybe the eye here, the chest, that's what has the biggest impact on the classification and the prediction. And if you have a different kind of dog or different kind of cat, you see that there are different kind of areas where the importance, so different kind of areas where we find out that the convolution narrative find out, okay, here's a pattern, here's something that is specific for the Maltese dogs, so the small dogs, and so on. Okay, so I know I don't have too much time. What is the proposed solution that we we are implementing now? We use that's what you get if you go to the ISIC database. You will get only this kind of images, so a typical dermatoscope image, a regular image, which is actually an image that we get using a typical wavelength of light, so the visible wavelength of light. What we can do, and this is what we also do, we provide more than just one image based on different wavelengths of light. And based on that, the skin is actually reacting differently, and we get more images, like here, the collagen, for example, or the hemoglobin. So we can extract much more features from this kind of images, because one mole means 5 images. And we can go, it's not really a multi-layer because it's not really exactly, the skin is not really built from, exactly layers. Like here, it's more like it's more a more complex structure. But there are some blood vessels or hemoglobin here. There's collagen here inside, the melanin that you have in the skin, and each of these kind of cells or cells, it's reacting differently to different wavelengths of light. So that's what we do, and what we do, we automate the scoring methods that are used by the doctors. So you have different kind of scoring methods. There are plenty of the scoring methods. 20 years ago, there was only ABCD. Now it's ABCDE. So asymmetry, border, color, and it was diameter. Now it's differential structures, and E, it's the evolution, how the mold changes in time. And there are different other methods that are used by the doctor to find out if this is a cancer or not. Based on the scoring value, they will just find if it's not a skin cancer, a suspicious one, or it's definitely a cancer. So they said also the priority should be make something with it or not really. And what we do, we automate the whole process. So now we have automated the hunter score. I will show you in a minute how we do it. We have also the 7 checkpoint list almost done. The ABCD, not E, because we don't have such a data set to really cover E, but ABCD is already covered, and some of the other methods as well. Here you have some examples of patterns that we analyze. So here you have the brain pattern, which is a pattern that say, oh, that's not a cancer. In most cases, it's not a cancer. Here you have the blue veil here. It's kind of a black-blue pattern, and this means it's a very advanced cancer. Or you have here the dots here, that's also advanced cancer. And these images are done with different wavelengths of light. I mean, these two are the same one, these are a different one, and also here, this one is a combination of 3 other ones. So this is actually how deep it is going into the skin. Okay, so the demo, and I'm done. So the pre-processing demo, and let me show you some of the examples here that you have already.
Karol, let me very quickly jump in here. You can either do the demo and no questions, or you can go straight to questions. But I'm afraid we're out of time, and we need to then move on. But I'll leave the decision up to you if you'd rather take questions or rather do the demo.
1 minute demo, 2 minutes questions.
Okay.
Okay, so here's the demo. It's easy. You can find out it on the GitHub. It's easy really to find out the image. Here it's a really nice cancer. You see the blue stuff here also around. It's really advanced. And if you go into other notebooks that I have shared with you, you can use some of the methods that are also here explained. We use different kind of, for example, we can use the histogram here to find out how many blue colors is actually on this image, for example, right? Or even use autoencoders here to find out. Here you can see, okay, that's fine because it's more blue. It's more red than blue. That's good. But if it would be more blue, then it means, oh, it's not really how it should look like, right? And obviously we can use different models of color. All right. So what we do, there are four different notebooks you can go through and check. The really basic image pre-processing methods that we use for getting the ABC covered. ABC method, scoring method. What we also do use fractal methods to find out the borders, for example, here. Right? You can see it's quite fine compared to this one. Right? So we use also fractal methods to find out the border, for example, or the shape of this specific pattern. And that's how we do the whole image pre-processing to get the features outside instead of a convolutional neural network to find out the patterns. We have more than 30 different patterns to that you should cover, or we should cover in the whole process. Now we have used SVM and decision trees. We also use convolutional neural networks, but the neural networks in general, they are quite hard to explain. So we, for now, a typical, not convolutional neural networks, so we don't really use it for now for the FDA approval. Some of the papers that I would like you to show that you can read, some of them that I have published, and some of research papers like expert system of applications. Find it on internet, adding my name, Karol Przystalski, and skin cancer in Google. You will find several papers. You can read it about skin cancer, how to analyze it. Yeah, Q&A. This is the part where actually you can ask questions. Thank you.
Okay, that was a little bit more than 1 minute demo. There's one question that I thought was quite relevant given the amount of time that you spend on the FDA part. So there's a question on what's the level of explainability needed by the FDA?
Mm-hmm. You should think about persons. Well, you should think about the people from the FDA that they don't need to be experts, right, in healthcare. Even they might be, but you should think about them like explaining them like it would be your, I don't know, your uncle that is not really a medical doctor, to explain step by step what's going on in a way that the person will say, oh yeah, I understand how it does work, so I'm fine with it. So there is you can use one of the methods, explainable methods that I showed to you before to make it, to go through step by step. And there is a lot of documentation behind it. So don't think that it's just one sentence or just one page to explain it. It's really, in many cases, it's just many pages that you need to write to explain it, visually, text, and so on.
Okay. So then let's thank Karol. I don't know, I guess we virtually clap. And thank Karol for the presentation. The links to the notebooks that he was showing are available on the meetup page. If you go to meetup.com and search for PyData Berlin, go to the June meetup, you will find the links there. Now we're going to take a little break, but we will not cut the YouTube stream. We have a program number for the break, and for that I yield the floor to Noah and Theo, and I believe also Jim.
Yes.
Yes. So
Noah,
hi everyone. We decided to try this meetup, a different structure for the lecture, or for the break, where we are gonna have some short conversations or presentations from about PyData and NumFOCUS and about the community that we have here. And maybe you can also, if you have questions, write them in the chat, and then maybe we'll give you the floor to speak and have more of a conversation. We are gonna start with the presentation of NumFOCUS, what it is and how does PyData and PyData Berlin fits into it, from Jim, who is in the far away United States, hopefully corona-free. And
not the farthest away though. It would be a little bit of a shame to send Jim some PyData stickers.
PyData, yeah.
Yeah, so, no, we don't need that. I have more than enough stickers to keep me busy for a while. So
exactly.
So if you want to try to claim stickers, of course, please send us an email to info@pydata.berlin with your location, and if you're lucky enough, you get the stickers. Yeah, and after the short presentation from Jim, we will Theo will have a conversation with two of PyData Berlin organizers. Yeah, and please feel free to write down questions, and we will give you the opportunity to ask them. Yeah, so Jim, the screen is yours, I guess.
Yeah, awesome. I will share my screen. Hopefully you see that. But yeah, more to the point,
Yes.
I Can you see it should say NumFOCUS and PyData, right? We good?
Yeah, we see that.
Okay. So yeah, thanks for inviting me. I'm always happy for the chance to talk about PyData and NumFOCUS, and in particular, it's for those I probably unfortunately haven't been able to meet a lot of you, and would have loved to meet you in person at a Berlin conference this year, and unfortunately I was not. So happy to meet you virtually. My name is Jim Weiss. I am the NumFOCUS events manager. People understandably often wonder, like, what's the relationship between PyData and NumFOCUS, or, you know, even what the heck is NumFOCUS? And so here's just a quick overview, and happy to answer any questions afterwards. But NumFOCUS it's a nonprofit organization. We are located in Austin, Texas, in the United States, which seems to be one of the further distances from this meetup, but glad that it's not the furthest distance, so that we can give out more stickers. And, you know, I always joke that NumFOCUS is more than just a sticker company. You know, we have a couple of key missions that I'm happy to talk about here, that includes, but is not limited to, giving out a lot of different stickers for your laptops. So our mission focuses on two main areas. One, we directly sponsor 35 open source projects in scientific computer programming, and that number is always growing. And these projects, a lot of people know and use, like Pandas and Jupyter and NumPy and SciPy, Matplotlib, Bokeh, and you actually see the full list here. And I invite you to take a look and see how many of these projects you recognize and or use. Some are widely used, some are used some in kind of like niche sectors, but are still vitally important to the work being done. And so that's kind of our one focus of our mission, is directly sponsoring these projects here. And the second part of our mission is to support the community of users and developers of those open source tools. And that's where PyData comes in. PyData is a program of NumFOCUS. The mission of PyData is to provide a forum for the community and users to learn from one another. We do this in a couple ways. Each year we host conferences all around the world. PyData Berlin is one of our flagship conferences. It's one of our biggest, but we also have conferences across Europe, in America, South America, Asia, and we're always looking to expand to new areas. And of course, everyone here is aware we also host PyData meetups, and we currently have 173 different meetups from across the globe in 61 different countries that are all organized and run by volunteers from the community. So very, very important. And one of the important things we like to share is that any proceeds that might come from PyData events to are used to continue to support our projects. So anytime you attend a conference or make a donation, that money will be used for things like small development grants, financial services, legal services, operational help, promotional support, and a whole wide range of things that we do for these projects. Because we know these open source tools, we all use them, but they take time and effort and dedication from volunteers that contribute to them. And the support to NumFOCUS provides us a way to support those projects, enable them to, let them focus on what they do best, which is continuing to develop and contribute to these projects to make them better. So, I always like to first say, thank you to everyone for joining these meetups, for organizing, particular thanks to the organizers and volunteers that help put on these community events. Any type of contributions go a long way in supporting our mission. And like I said, I'm bummed I won't be able to see you in person this year, but if you have any questions or you're interested in getting involved, in addition to potentially reaching out to the Berlin meetup organizers, you can always email me directly, and my email address is jim@numfocus.org, or you can email admin@pydata.org, and we'd love to have you and get you involved. And like I said, we're always looking for volunteers or other ways to have people get involved. So here's just a few ways. You can participate in a local meetup, which everyone here is doing. So already off to a great start. Thank you. And these meetups help share ideas. We can learn from one another and just give people an idea of what they can take back to their work and continue to improve and figure out ways we can even improve the tools and help support them. You can attend a PyData conference. Like I said, money from every PyData ticket sale is a donation to NumFOCUS to continue our mission, or even volunteer. Our organizers can probably have more than enough to say about some of the work that the volunteers do at the different conferences to make sure that they happen. I would encourage you, maybe consider making a donation or getting your company to either sponsor a PyData event, or NumFOCUS itself has a corporate donation program that I'd be happy to talk to you about as well. And so we're always looking to partner with corporations, because corporations often use and make money off of these open source tools. So if there's a way that they're able to give just a little bit back to the open source community, that can go a long way. And so, like I said, any questions, any more information, I'm happy to kind of open up a conversation or talk more. And you can either visit our website, numfocus.org, or email me or admin@pydata.org, listed there. And thank you. So that's what I have.
Yes, thank you very much for the kind intro to NumFOCUS and how PyData fits. And now from the macro, let's go to our micro PyData link. Theo?
Yeah. Can everyone hear me?
Yes.
In a way or another? Yes. Okay. So I would like to first ask two people who are currently involved, do two interviews with people involved in the PyData Berlin chapter. So like to give you an idea of who we are, and also maybe join us, or maybe create your own whenever you are. So first, do we have Valentina?
Hi, yes.
And you? Yes, great. So I have a really simple question. So first, hi Valentina, can you tell me a little bit quickly what you are working on right now? So what are you doing, basically?
Yeah, so right now I am a software quality assurance engineer. I studied astrophysics and I'm still an aspiring data scientist. So yeah, I would like to be a data scientist, but I'm programming quite a lot also in my role.
Mm-hmm. Cool. Yeah, so now can you tell me how and why you become involved in the organization of the PyData?
Yeah, so that's because when I terminated my PhD, then I went to industry. I didn't have any experience in industry, and I've been interested in data science since. That's like about 7 years ago. So I started. I found out that Meetup was the best place to actually learn about industry, people, networking, eventually find jobs, all these things that I never heard about before. And I started going to the PyData meetup as well. And then I was really happy there. And I remember, I don't know if it was like four years ago, maybe, that I joined the call for volunteer for the conference. And I had a very beautiful experience. And so the year after, when I was asked to join the committee, I gladly accepted the invitation. And since then, I'm volunteering mostly. Now I'm mostly in the conference coordinating the volunteers. But yeah, since I've been in that role, it fits me. I don't know. And it's also a way to give back to the community, because I've been learning quite a lot.
Great. Super. Last one. What's your favorite place in Berlin? So during this Corona time, do you have a favorite park or restaurant to go to for all the Berlin?
I don't have a real favorite place, but I'm actually going by bike a lot, which is not it was not my thing. I haven't taken the bike since years, and now suddenly I'm going everywhere by bike. Mostly also because I'm looking for a new flat. I'm traveling here and there. Just today I went somewhere and then back and then continue working, and yeah. But also since not so long ago, some of my favorite restaurants opened again. I've been also going there. There is one around the corner. It's Italian. I'm Italian. From Sicily. No, the restaurant, not me.
Yeah.
So yeah, these are the places like bike rides, parks, and my favorite restaurant. Not that much.
Yeah. Definitely. Biking in summer in Berlin is really cool. I agree. Okay, so thank you very much, Valentina. I will just ask the second one. Adrian, are you here? Can you unmute yourself?
Yes, I am.
Perfect. Hey, so no surprise, Adrian, can you welcome? Can you tell me what you are working on right now, please?
Finding a job is one. Otherwise, I work mostly on scikit-learn, and otherwise sometimes on FairLearn, which is a fairness in machine learning initiated by Microsoft. Yeah.
Great, that's good. And so, can you tell me why you decided to join and to be involved in PyData?
I was just looking for a bunch of cool people, really. I moved to Berlin 4 years ago and started immediately going to meetups. Like, moved to Berlin, opened the meetup app. I was like, okay, where can I meet people? And then among them were a bunch of technical meetups. I used to go to a lot of them. And out of all the ones that I went to, PyData was the friendliest, with like a bunch of really nice organizers. And then we ended up being connected and started working on the meetups and the conference.
Cool. And last one, favorite place in Berlin? So during Corona time, or ice cream dealer for you, maybe?
No, I've been going to a bunch of parks around in Neukölln, but otherwise, if it's an evening, if it's close to the weekend, I'm out. I'm probably in Friedrichshain, going out to different places when the bars and pubs were not open, just going from Späti to Späti. And now you can actually spend time there, and that's usually where I am.
Cool, great. Okay, thank you very much, Adrian.
Thank you.
I think that's it. I was the first try that we did. So please tell us in the comments if you think that was interesting. If you have any suggestion, that they are welcome, that we can do during the break that you are interested in. Otherwise, let's go for the second talk, and I will give back the talk to Matti. Here we go.
Thank you. Yeah. Okay. I hope that break sort of gives some more insight into who we are and how we work and what PyData is and what NumFOCUS is and so on. If you have any questions, post them on the chat, either on Zoom or on YouTube. We'll try to answer them as best we can. And Also, if you think that you are the furthest away from Berlin from all the participants, then write that in the chat as well. We will send some stickers to the participant who is the furthest away from Berlin. I think currently the Philippines is winning. Okay, and so with that, I give the floor to our second speaker, Andres.
Thank you.
Go ahead.
I will share the screen then first. 1 second. Okay. Okay, so just everybody's, is it okay? Are you seeing my presentation now?
Yes, I'm seeing it.
Yes,
Okay.
We can see your presentation.
Okay, perfect. So first of all, hello and thank you for being here. For a very, very short introduction of myself. I studied architecture. Now I'm currently doing a master in project management and data science here in Berlin. I didn't do much of architecture. I started a software company, then another one, and now I work as the CTO in a Latin American company that is dedicated to providing tools for closing the gender gaps in the workplace through technology and data. That was a very brief explanation of who I am, and let's get started with this. So some expectation management first. My talk is going to be more theoretical, and the main aim is to introduce you all to the main concepts, processes, and techniques behind time series analysis and forecast. So the agenda for today is first to have a look of what we know so far, then take a look into what makes time series so special, and finally a short overview of how to handle such thing. So let's get started. When we're in the non-time series world and we're dealing with cross-sectional data, there is a very big assumption that there is a population from which we're taking a random sample, and from this random sample we can make some assumptions. So we have many observations of the same variables through time, and these observations are independent from each other. So for example, here, the student 1 grade should be independent from the student 10 grade or age. These observations are generally taken at the same point in time. This means the same year or the same period, or to be more precise, time here is not relevant at all. And we assume from the statistical theory that these random variables follow a certain distribution. This gives us some kind of explanation of what we can expect. So if we do some measurements, we can somehow interpolate the data and we can understand, oh, sorry, 1 second. And we can make some assumptions about what is happening in the rest of the curve. In the world of time series, the main difference is that there is not such thing as a population. Here, what we have is different samples of the same process through time. And this gives us at the end a discrete series or sequence of data points. These have been taken in a regular or constant interval, and hence the target variable y, it's indexed by time. Time, of course, being an independent variable of which we have no control. This all leads to something very important in time series, that there is an underlying structure. In this case, we do care about the order of the data. If you remember the past example, it doesn't matter which student we measure first. At the end, we get the same data set, and we don't care. Here, the underlying structure is very important, and we need to maintain it. So this is going to be one of the directives of time series. Finally, everything that we do as a prediction, meaning forecasting, looking into the future, is going to be an extrapolation of our data. So this means there's some uncertainty on what we're doing, or to be more precise, there's more uncertainty on what we're doing. In a very simplified way, our target variable is a function of time. This just means that knowing the time, we can go backwards and know exactly which is going to be our value. In this simple case, this is the energy consumption of the United States. So if I tell you a date, you can go with the function of time and understand exactly how much was the demand. A more important concept of time series is that sometimes you will hear that a time series is an stochastic process. What this means in more simple words is that we have, in our case, we are seeing, or data represents one possible outcome of many. But since we cannot go back in time and run the process many times, as stochastic processes imply, meaning that all these different runs come from the same process, but they are like parallel things that happen, we cannot do that. It's not realistic to think that we can go to every single point in time and have all the possible observations. So this one will never happen, because if you think it through the theory, what happens in stochastic processes is when you run many, many times the same process through time, you end up with something like what we saw before. You have a distribution. And these facts add even more uncertainty to time series analysis. And this is why, for example, we have concepts as the stationarity. The stationarity in the practical way is saying that the mean and the variance of a data set, meaning the statistical properties, they don't change through time, or they do not change systematically through time, to be more precise. For example, here you can see that this is non-stationary, because as far as you go through time, the mean is going up and the variance is every time more and more. On the other hand, here we can see a stationary series, and it doesn't matter when you take the measures, you're going to have roughly the same measures of mean and variance. And this is what we understand as the stationarity, or weak stationarity, to be more precise. Stationarity is very important, mainly because most of the models we're going to use in time series assume that your data is stationary. So if it's not, you will have to do some kind of operations on your data to make it stationary. There are many ways to do it. For example, you can take the logarithm of your data and that will stabilize the variance, or you can use differencing, that is just looking at the difference between points and not the points themselves. And this also helps towards taking your data towards stationarity. Of course, you have the statistical tests that will tell you if the data is or not, but mainly you can see from, like we saw here, visual inspection is already quite a good place to start. Other characteristics and attributes of time series. The level. The level is nothing else than the mean of our data set. The trend. The trend is a long-term increase or decrease in the data and is not necessarily linear. I think most of us are now familiar with the coronavirus exponential growth. This is also the trend, but it's just not linear. Seasonality may be one of the most important things that we will talk about today. And this is a pattern that repeats itself over time. And it's when the variable is affected by a seasonal factor. Seasons, in this case, we're not precisely meaning winter or summer, but seasons is more something regarding time. So there's a causal relationship between the measure that you have and the point in time that you take it. Yeah. And of course, what is important is that there is a known frequency, and it's the same one. It can be anything from years to minutes, but it's repeated and repeated again. Cycles are similar, but in here you have the property that you don't know the frequency. And normally you will see that the trend and the cycles are going to be integrated in one variable that is called the trend cycle or cycle trend. And it just shows the overall movement of your series. And finally, the white noise, as is known in time series, is just all the information that your time series have that is non-explainable, that is caused by chance or randomness. And it's supposed to be normally distributed. This means that if we explore all the possible values, we will have something like this. So going back to seasonality, how does seasonality look like? So, for example, here in our example, we have the energy consumption through the years of the United States. And you can clearly see that there's a pattern that repeats itself through time. So this year and the year and the year and the year. This is called a yearly seasonality. But you can also see it, for example, if you look at the same data in a zoomed way, the same thing happens. This is the day so from 0 hours to 24 hours, and you can see that every day something similar happens. This also is a seasonal pattern, but in this case we have a daily seasonality. This is why it's so important to know what is the measure of your data, the units that you're dealing with. So because sometimes you will deal with years, sometimes you will be dealing with microseconds. Most of the time, it is important to analyze the time series from the perspective of each one of these components that we just talked about. And in order to do so, we do something called the composition process. To do this, what we assume is that our time series is a model that is the sum or the multiplication of the three factors that we already saw. So you can either add the trend, the seasonality, and the residuals, or multiply it in other kinds of models. And this will give you something like this. So you have the trend, the seasonality, and the residuals. And if you add them up, you should reproduce your data. There are other kinds of decompositions, for example, with Fourier terms, that is more the sinus and cosinus, but this is a little bit more complicated for this talk. And of course, the multiplicative one, thanks to the logarithm and its properties, you can take the logarithm and just treat it as an additive series. So this is going to be also an important tool to have in the toolbox. Remember that the white noise we talked about is the same as saying residuals. It's the same term. This is interchangeable in time series most of the time. Another thing that is important in time series is that instead of looking for correlation with other variables, as we're used to, we're going to look of correlations with the variable itself, just backwards in time. And this is known as autocorrelation, because you're correlating the variable with itself. And how does this work? Let's say, for example, that this is our point 0 in time, meaning the last measure we took of the demand. And we're going to look, what is the correlation between now and 1 unit back in time? And of course, you have to repeat this process, 0 with 1, 1 with 2, 2 with 3, like going one step back. And you will get something like this, a scatter plot that will show you what is the correlation. And you see that in this particular example, whatever the consumption or the demand was now, it's very likely to be the same that it's going to be in the next unit of time. So there's a very strong correlation. Also, in the case of demand of energy consumption, if you look 24 units of time in the past, in our case, hourly data, so if you look 24 hours in the past, it's very probable that the consumption is going to be the same because the conditions are the same, the weather, the time of the day, people is at work or not. And you can also see that there's a certain correlation. So this is what is known as autocorrelation in time series. From this same principle, we developed what is called the lag variables. A lag is nothing else than a period of time between one event and another. And in our more precise example, it means that you can engineer features by looking back into time. So let's use again our example where we are standing here in time. This is our last measure. And we need to engineer features that are like what was happening the hour before and what was happening 24 hours ago. So to build this data set, we're just going to shift one up and take the value. We're going to shift 24 times our data set and have a new value. And this here is our new data set. If you think it through, these two engineered features come from this, just looking into the past. And this is also very important and very particular to time series. If you remember correctly, normally you're thought that correlation between predictors is not a good thing, but in this case, it's precisely what we want. Regarding data exploration, we have many very particular visuals to time series. The first one being the time plot that we read so many times. And what are the axes here? You have time and whatever is your dependent variable. So again, this reminds us of the y being a function of time. Also, you have this kind of plot that is very interesting and gives you a lot of insights that is called the seasonal plot. In this case, in this particular case, we are looking at the day from the 0 hour to the 24 hour, but we want to see how it looks that same day through the whole year in each of the months. So this is one day, like the average of all days of December. This is the average of all the days in January, etc., etc., etc. So this gives you a very good explanation and a very good overview of how similar things happen and how similar things are across different aggregation functions. In this particular case, you can see that the curve of demand is pretty much the same during the whole year. There's only a slight trend. In this case, the trend is that it goes up to December and then it goes back to May. This is, of course, linked to the seasons, winter and summer, and that's why also where the word seasonality comes from. There's a causal relationship between the measure and the time of the year where it was taken. Another kind of way of seeing this is also a seasonal plot, but from sub-series, is this one. And in this example, we are seeing the aggregated data for January, all the aggregated data of January for the year 2016, the year 2017, 18, 19. And this gives you a very clear overview of what happens over the years, because you can see also that, for example, here, May is the one with the lowest consumption in general, this is the mean, and December is the one with the highest consumption in general, and this is the mean. So this is also a very useful tool. And you can see, of course, the pattern through the year that is also kind of very clear here. Scatter plots, as we saw before, is also a tool that you will use a lot. And the only difference here is that the scatter plot is not between our variable and another one, but the variable at itself in the past. So here we can see 3 examples. Again, energy demand is the example here. You have now, and now related to -1, or in this case +1, because that's how the Python package plots it. And you also have 24 hours ago and 10 hours ago. If you think it through, in our example of demand, is very logical, because of course the consumption now is very, very likely to be the same or similar to the one 1 hour ahead. And it's also the same, likely to be the same one as 24 hours ago, but doesn't have any relationship with 10 hours in the future. There's no clear relationship there. After talking about the same correlation, these may be the 2 most important tools that we need to understand and really get a grip of to work with time series. I will first explain the axis. The axis X is the steps in your data. So these will vary depending on the data you have. In my case, and in this example, I have hourly data. So every one of this means 1 hour into the past. And this here in this axis is just a normal Pearson correlation coefficient. So this graph will always start in 0, meaning the present, and they will start doing correlations to 1 value back in time, 2 values back in time, 3 values back in time, etc. If we look at a more particular example, it's the same as saying, like, I'm going to stand here and look 24 hours back. Then I'm going to start here, look 24 hours back, and the same. And this builds this autocorrelation function, because how this plot is made is that you have your data set and you just shift it 1 unit and then do a Pearson correlation between these 2 variables. The partial autocorrelation function is a little bit more complicated, but what it means is that it shows you the direct effect that the lag has on your today variable, meaning that in the autocorrelation function, whatever happens here has a relationship that goes like this, like it's like a chain reaction. But in the partial autocorrelations, you're directly looking, like you're making big jumps between what's happening now and what is happening 24 hours ago, etc. So it's the same principle, but just done differently. And how do you produce this? You do a linear regression with all the lag variables, and then the coefficients, the betas of your linear regressions, are going to be what you plot on the y-axis. So just before continuing, in my example, we know that energy consumption is very similar 24 hours ago. And we can see that very clearly here when you go 24 steps back in time. You can see that there's a very high correlation, the same here, this is still significant, between now and 24 hours. And also you can see that the first one is very correlated, and you can see it in both plots. This is a little bit of residual, so that's why we use both plots at the same time, to know exactly which lags we should use in our models. Regarding data preparations, there are some things that has to be taken into consideration. First of all, the trees rule as we know it doesn't work in those cases, because here outliers may carry information. Something may have happened at this moment in time. And for example, here, if you think it through, it kind of responds with a certain pattern that we're looking into the data. So just plainly taking it out because of the trees rule doesn't make a lot of sense. What can you do? The simplest model here is to use a moving average. And if this is the rough estimation of what it should be. And if you look at it thoroughly, you see that this will be included in our moving average. So it will be a mistake to use the trees rule normally. There are some more advanced methodologies, for example, the ones that Facebook Profit Package uses to do anomaly detection. But in simple words, anomaly detection is to identify patterns, and if something is significantly off of this pattern, it is going to be considered an outlier. As always, expert knowledge is very important here. For example, the World Cup. You may have this can be the World Cup and the consumption went up like crazy, but it's just one point in time. So this one you can really take it out of this data set because it's not important. Another thing to take into consideration is that missing values, they cannot exist in our data. So we necessarily need to do something with them. We need to impute them. There are many ways to do it. The simpler one will be to use the mean or a zero value, but of course this will depend on the specific case that you have. Another more used approach is to interpolate the data, and this is just drawing the closest line between these points. Of course, you can also do the last observation carried forward. That will be take this point in time and like this, or you can use something more advanced like KNN, mice, whatever other technology that you want to use. Of course, these ones, you need a multivariate data set, because when it's with your own data set, it's not that easy. 1 second. I'm going to answer the question now. I think it's a good question. Give me 1 second. So the thing, as I said before, the missing values are forbidden because precisely here the structure is so important and there's an underlying thing happening. So if you think it through, time doesn't stop because you don't have one measure. It doesn't mean that that day or that hour didn't exist. So when you take out that value, you are destroying the time structure behind it, which in cross-sectional data, it doesn't really matter because if you have one row less, it's just, you can assume the rest of the shape as we discussed before. So here is very important to maintain always the time structure. So if you have minutes, you need to have every possible minute. Of course, there's a logical constraints. You cannot go to milliseconds, but you will try to fill the whole data set, of course, inside the same unit that you're already handling. Another consideration, and I think this is maybe the most important one, is regarding the splitting of the data sets for test and training. The golden rule here is you cannot look into the future, hence the sample must not be random, because if you think again about the example of the students, you don't really care what rows do you get. At the end, it's even better. The more random you do it, the more certain you can be that your predictions are right. In time series, sorry, if you look into the future, you're somehow cheating. So you really need to be sure that your split is time-based, meaning only looking to the past. It should also include full seasons or cycles for the seasonality. If you don't include the whole cycle of the seasonality, the models cannot understand what's happening. And this is another important thing. They have at least to have the length of the longest lag. What do I mean with this? If my model, for example, depends on the 24 lag, this means that I depend on what happened 24 hours ago. I need to have at least 24 data points to predict. This is a very absurd case because, of course, I have more than 24 data points. But when you're talking, for example, about data sets that have years, it's not that obvious. So yes, maybe you have a very nice correlation between 3 years ago, but what happens if you have only 10, 30 points in time? So this is just to be taken into consideration. And from my point of view, it also should be logic, easier for humans to understand, because machines, they don't care, and for them time is nothing. But for us, it's better if you cut in precise points, meaning, for example, the 1st of January or the whole year, the whole month, and not cut in the middle like 15 or 14 of May, because maybe for the machine it doesn't make any difference, but for you it's going to be harder to interpret later. Feature engineering, as we discussed before, we can derive a lot of things from the time index, meaning the time in which the measures were taken. You can have a lot of nominal values, for example, month. It can be encoded from 1 to 12, the day from 1 to 31, hours to 1 to 24, etc., day of the week. And you can also have dummy variables for something like is month start or is leap year, which in cases of business problems, it can be something that is relevant for your particular case. Also, you can engineer the demand lags that we talked before, and this can be simple ones. For example, like one can be what happened 24 hours ago, or like for what happened 14 days ago, but you can also do rolling average of what happened in the last week. So you take the whole last week and you make a rolling average, sorry, and you keep doing this average, and this produces a new data point in your data set. Something to take into consideration when you add exogenous variables, meaning you have your variable, and for example, in consumption of electricity, you add the weather, which is known to be a good explanatory variable. You have to take care with these cases that about what is called spurious correlations. meaning that there's a dependency to time, but not a dependency to your variable. A very simple and clear example of this is the size of a tree and the population size of a country. They don't really have any causal relationship between them, but if you look through time, both they tend to grow. So you can be fooled by this. And now we get into something more down to earth and practical, modeling and forecasting. So first of all, and the simplest way, to tackle this problem is just to use a normal multiple regression. To do so, the first thing is to completely disregard the time index. We're not going to care about it anymore. Of course, this is after train and test split, because there we really need the time index. And if you look at it closely, you have a target variable and you have features and predictors. So this is just a normal data set like the ones you're used to do with machine learning. So this is one of the approaches that you can use as a baseline. Of course, there are baseline models that are simpler and more related to time series. The simplest one being the simple naive. They are called naive because they make very simple assumptions. The first one, what it says here, this formula is that the value of tomorrow is going to be the same value of today. So an example would be, if I sold today 5 ice creams, I'm going to assume that tomorrow I will sell also 5 ice creams. And then tomorrow, and actually I sold 8 ice creams. So the next day I'm going to say, I'm going to sell 8 ice creams again, and so on and so on and so on. The trend naive is very similar to this one, but you add a little bit of the drift towards increasing or decreasing. For example, if your business is growing, that you know that maybe today I sold 8 ice creams, but tomorrow it's going to be 9 and 10 and 11, but there's a particular trend that you can infer from your data. And you would do it by looking at the past. So you can clearly see how the things is evolving. And finally, the seasonal naive is the same as saying, okay, today is Sunday, and I know that whatever I sell every Sunday is what I'm going to sell the next one. So I just look into the data 27 days ago, and this is my assumption for the next day. If we go into a little bit of more complex models, we have to first remember what is a simple regression. We have our predicted value, and this is going to be equal to some intercept plus a coefficient times our input variable. Yeah. So if we translate this principle to time series, we have 2 models, which are the basis of most of time series forecasting. We first have the autoregressive model, which is normally seen as ARP. P is just the order of the model that we will understand shortly what it means. And we have the moving average model, or MA, order Q. Q also is what kind of model we're using, because this is a family of models. The autoregressive is nothing else than doing a simple regression of our variable, but looking into the lag variables. So, for example, an AR1 model will be my YT is equal to a constant, exactly like here, but plus some coefficient multiplying my lag value in one time in the past. Of course, there's always some kind of error in our predictions, and this is incorporated in both models, and this is going to be there no matter what, because there's some randomness on what's happening. And the autoregressive is just a simple linear regression on the lag values. On the other hand, the moving average one is a simpler linear regression, but not on the lag variables, but on the error of your past predictions. So, for example, yesterday I predicted that I was going to sell 10 ice creams, but I actually sold 8. So I have an error of 2 units that I didn't understood. So those 2 units, I'm going to put them into my machine, this model, and they are going to help me understand what's going to happen next. This is called a moving average, because normally you are, for example, I always sell 10 ice creams. That's my average. This is what I know. And basing myself on the errors I make every day, I'm going to try to adjust around this average to see how much I'm going to actually sell the next day. Then we have the ARMA and ARIMA families that maybe you heard of if you have been looking into time series analysis. This is something that I'm sure will come up. And the ARMA is nothing else than combining the past models we saw. So it's the same as saying AR model plus the MA model together. In this example, an ARMA 1,0 model is the same as saying AR1, because the MA part has a 0 order, meaning that we don't take care of any error, we don't care. The same goes for an ARMA 01 would be the same as saying a moving average of order 1. Yeah. So this is just the addition of the literal addition of these two models. ARIMA, on the other hand, it adds something else that we haven't seen before, and it's this little I in the middle, or which is represented by the D. This is called what is the autoregressive integrated moving average. The I of integration, what it does is to do a differentiation of our time series. If you remember, I said that one of the main assumptions made by the models is that the data is stationary. So if it's not, you must do something in order to use any of these models. So you can do it yourself with the logarithm and the differentiation, but also the ARIMA model helps you and do it during the process. So you can have an ARIMA that has an autoregressive part and one as differentiation factor. So that means that you're going to differentiate one time your data and then run the AR model. So this is what the ARIMA stands for. And here we just start adding letters to our model, and the S of SARIMA is the same, but it has into consideration a seasonal component, meaning it's like kind of the same as saying that we have two ARIMAs. So this is the ARIMA that we already know, and we're just doing it. We're doing this process twice. So one in the close past, and the other one is looking back a certain amount of time. So for example, a SARIMA model with a seasonal component of 24 will be like, I have an ARIMA, and then I look again into the 24 lag, and I do another model again in the past. It's a little complicated, but just think about it doing 2 times the same thing. And finally, SARIMAX is the same, but we add an additional layer of complexity, which is the exogenous variables. For example, the weather, as I talked before. So this is the ARIMA family. This is, I think, one of the most common models to predict time series. This is the definition of differentiation. So you just take the value of before to the value of today, and what you end up with is the series of differences. Finally, I'm going to talk about recurrent neural networks, but I'm not going to go into any detail because this is a talk by itself. And you know that from language processing, that Matthew will tell us, the order of the words, meaning the order of our sequence, does matter. It's not the same to say I'm a human, that same human am I. So this same idea was transferred from the language processing world into the time series 1. Because if you think it through, you have a series of things, of X's or inputs that matter the order in which you understand them, and you have some sort of prediction. So for this, mostly you will see people using long short-term memory recurrent neural networks, or what is called the GRU, gated recurrent units, which are kind of similar in principle. Of course, I've also seen some people using convolutional neural networks, or you can also use a normal deep network to do a multiple regression. This is another option, but I think it's a little bit overdoing it. And this is how a modeling pipeline could look like. So you can decide which is your baseline, can be one of the naives and one of the multiple linear regressions. And of course, if you cannot do better than this, or significantly better than this, then just continue and do something else, because it doesn't make any sense to add such complexity to go all the way here if you're not going to get a significant improvement. Finally, how do we evaluate? And there's a very important concept that it doesn't come up in other domains, that is the walk forward. First of all, we need to define what is an error, because the calculation is simple, observed minus forecast, but these always have to have a business meaning. In the case, again, of consumption of energy, what is worse for your company? Is it worse that you overproduced energy, or that you don't have enough energy for the city? So this idea of what the direction of the error means for my business is very important, and it's something you should have clear from the beginning. And metrics, we have the same ones that we normally use: the mean absolute error, that is a very good business metric; the mean square error, that is good for algorithms because it's very fast to calculate; the root mean square error, that is kind of the same but it's good for us because it's more down to earth and it's very, very, very sensitive to extreme error, so it's good. And finally, but not least, we have something called the Akaike information criterion. This is just a measure that will tell you how parsimonious is your model. And this is good to know because, for example, for the ARMA or the auto-regression models, if you remember correctly, in the graphs of the PCF, there are a lot of lags that you could use because they are significant. But of course, these archaic information criteria is going to tell you how many of them it is necessary for your model to be accurate enough. So at the end, what this does is uses the likelihood of the model representing your data, so how good the data fits the model, and it has a penalty for each predictor that you use. So the more predictor you use, the more penalty, hence the AAC, the lowest, is the one that you will look for when you're trying to assess the different models. Regarding the residual analysis, as we talked before, there's something very important here that is the forecast error. And what we want to see at the end of our forecasting is that there is nothing left, only white noise, because by definition, if we only see white noise, there is no more information left in our data. This is completely random, so we cannot explain it. Just one topic left because I'm running out of time. And if you do a simple in-sample forecast, meaning you look back in time, your model is going to do a quite good job to interpret your data. You can almost not see the blue line because they're practically the same. But if you try to do the same, looking into the future, these kind of things can happen. The data can diverge completely, going crazy. It can convert to the mean or to some value. But in general, you will start having a bigger and bigger and bigger error. Why does this happen? It happens because if we look at this example very quickly, and let's assume this is time 0, and we're starting here. Yeah, and we know that our model is going to look one step back in time, 2 steps back in time, and 24 hours back in time. So we have this. I look at the lag 1, lag 2, and lag 24. This is what I use to predict something. And each step I do, I have to look at these values. So if you see detail here, from the second prediction, I am already using my own prediction as a predictor for the next step. And this, of course, adds up. And there's a moment where you are making predictions only based on predictions. So of course, there's a lot of uncertainty, a lot of error that is adding up and is making your predictions go crazy. This is why we have to retrain, retrain, and retrain on what we call a moving rolling window. The principle here is that you do like this. You use this data to train your model, and you predict whatever window of time you need. What is the size of this window? It will depend completely on the business you're in, and in your, not only the business, but the problem goal. So this has to be defined from the beginning. What is going to be my window of predictions? In the case of energy consumption, we cared about 24 hours in the future, because it's what you have to pre-produce or kind of negotiate with the energy producers. And this, you start moving it through time. So every time you predict, then you move, and with the real values, you retrain your model and you repredict the next step. Well, and finally, you can use the same logic, but with an adjusted rolling window. Of course, this one is a lot better because you have more historical data that we all know that is better for predicting. But this has a downside, is that, of course, you will need more and more and more computing power. So it depends on your capabilities in that department. And finally, this is what a time series pipeline could look like. So yeah, I'm not going to go into detail because I think I extended myself too much, but I'll share the slides later if someone is interested. And thank you very much.
Thank you indeed. I'm gonna virtually clap. I don't know if anyone can see or hear that, but there we go. So questions. I think I'm gonna let because the YouTube stream is a little bit behind, there's a little lag. So I'm going to let that catch up and ask a question in between. So there's the first question already. Can this also be used for ECG analysis or electrocardiogram analysis? I'm not entirely sure if that's referring to the time series analysis in general or a specific slide.
I would say yes, because this time series universe is mainly focused on signal processing. So one of the biggest applications is for processing of these signals and electrocardiograms. I can imagine, as far as my understanding in EG goes, it's a constant signal that you could start identifying patterns and maybe even predict if someone's going to have a heart attack. But I don't know it from experience. I'm just saying that I think it's possible. It fits the criteria.
Okay. I was wondering, I was quite interested in what you said about the time series analysis field borrowing ideas from NLP in the sequence modeling area. And I was wondering if you have anything to say about the recent development in NLP where the sequence models like LSTMs and the gated recurrent units are going out of fashion, and the more kind of structural neural networks like the transformer model, like BERT and GPT-2, are very much starting to be the focus of research efforts. And there's some evidence also that those capture sort of linguistic, syntactic, semantic structure in a way that is kind of linguistically reasonable. I don't know what the equivalent of that would be on time series analysis, or if those models are being applied. I was just wondering.
To be very honest, I don't know it by personal experience. I've seen some talks about the transformer one, the transformer model, but I don't know much of it. I can imagine that for time series data, because of the structure is just one, so you care about the order, but the order is just one. It's not the same as for language processing, because there are many different orders can come into the machine, and you need to understand out of context which road to take. But I've seen people using the transformer to predict.
Okay, very good. Can you recommend a TSA book with a focus in Python?
Yes, I put in the last slide. I'm gonna put the two recommended bibliographies, at least to start with time series. The first one is in R, but at least for me it was a good Bible to start with this, because it has everything and it's very well explained, and it's not in Python, which I would love to, but for the conceptual part, I think it's very, very good. And then the second one that I'm sharing here in the comments, it is mainly for Python. It has a chapter for time series. These are both open source, and you can access them online.
Okay, maybe Misha, if you can post the two links, the two texts also to the YouTube channels, so that we get them there as well.
Yeah, sure.
Okay. Any other questions? Micha, if you're speaking, you are muted.
Yeah, there's another YouTube question.
Okay.
Whether it's always a good idea normalizing the forecasted data before giving them to an algorithm.
Andres, did you hear the question?
No.
Is it always a good idea to normalize forecasted data before giving them to algorithms?
That depends on which one you're going to use. I would say that the more traditional ones, they don't care. But of course, if you're gonna use any kind of neural network, it's better to at least scale them. You can also use the log transformation to normalize to stabilize the variance. But yeah, it depends. I think the answer there, it depends on which one you use and the kind of data you have.
Okay. Do you have any thoughts about automatic time series forecast packages like Prophet? You mentioned that in your presentation as well.
I think Prophet is a very comprehensive package. So for time series analysis in Python, it's a must. It's very well documented, and it has almost everything you can need. Some very advanced things, for example, the anomaly detection, it can be done automatically with the Prophet package. I'm more of a conceptual learner, so I think it's nice to first do it by hand and then use the package like that. But yes, it's very good, like for practical reasons.
Another question from YouTube. Have you ever needed to perform the ADF test for, I don't know how to read that, D-2 TS data integrated more than twice, I guess?
No, not in my case, but I know it's not uncommon to integrate more than once, to differentiate more than once.
I think the question was about integrating more than twice.
Then, in my experience, no. But I cannot know. Depends again on the data. But I cannot know. But I would my answer will be like, because we have the AIC criterion. If you integrate that much plus the AR coefficient plus the MA coefficient, you may broke what is called the parsimonious rule, that it's not supposed to sum up more than 6 all the terms that you use in your SARIMA or whatever model. You should have not more than 6. So if you have already an AR4 plus 1 order of MA, doing 3 integrations, it will be too much. And of course, like, you know, in any other fields, the more parsimonious, the better.
Yeah. And so Alan here on Zoom is asking one more thing. Have you used Kalman filters for forecasting?
No. No, I have no knowledge about it.
Are you going to make the slides available?
Yeah, of course. It's a Google presentation. I have to make it public, and I will share the link. Yeah. Okay.
Awesome. Well, then I think we are through with questions. Unless, Misha, you have one final one from YouTube? Nothing. Okay. Well, then, thank you very much, Andres. That was a very good introductory talk to time series analysis. That's it for the June meetup as well. Thank you, everyone, for joining. We don't know if the July meetup is going to also be virtual or in person. If it is in person, I think we'll try to maintain the YouTube live stream. We'll have to see how we can accommodate that, but if that's possible, then we'll definitely keep that up. But yeah, other than that, thank you everyone for joining, for the interest, and I don't know, see you next time.
Thank you very much.
Thanks, bye.